Good evening, everybody. Please confirm if you can hear me. Welcome to this free exclusive webinar series on 3D bioprinting. Welcome to the inaugural session, everyone. And I'm so elated to have you all on board here. Welcome to this power-packed session. Welcome to this important session where we are going to talk in detail about all the things related to bioprinting. Now, since you all have gathered here to discuss bioprinting, let me ask you a question. And the question is, do you know when was printing launched, electronic printing launched in this world? Now, this is a close association with today's session. I'll tell you how. Okay. So while you're Googling, allow me to also talk a bit about a similar story, but in a different industry. Okay. So the story goes like this. In the year of 1903, Wright brothers were the first to take the first flight successfully controlled powered flight, right? That's what Wright brothers did. And in 1969, humans were on the moon, right? July 20, 1969, the first person landed on moon, right? So you can see the difference here. 1903 to 1969, hardly 66 years. Now, let's come to our story, today's story. Printing was launched in this world. Commercially, electronic printing was launched in 1968. The first printer name was EP101. And in 2009, the first bioprinter was launched, commercially available bioprinter. Now, there is a similarity in between both the stories, and that is progress. Progress is the key word of our generation. And today, as you're going to witness our honorable speakers from Altem Technologies Private Limited talk about bioprinting, you'll realize how much progress our world has made in this digital era, in this electronic era. And ladies and gentlemen, it gives me immense pleasure to welcome all of you today to this session. Now, before I get started, quickly, let me know if you guys can clearly hear me, clearly see me. Yes? Okay, wonderful. So, people, this is one of the first industry-sponsored webinar series of this year. Okay, last year we had many, but for this year, this is the first. And I'm so elated, so glad to introduce to you Altem Systems Private Limited, the company which is leading in India today in terms of 3D bioprinter, right? So I was talking to the CEO of Altem, and we had a wonderful conversation 3 weeks ago. And we were talking about how exactly Altem wants to proceed and market this product. And that is where he said, I want to educate the young generation first about bioprinting, 3D bioprinting. And I was really impressed because if the CEO of the company thinks like that, if the entire team of Altem thinks like that, I think they are going in the right direction, because the student of today is going to be the user of tomorrow, the scientist of tomorrow, the researcher of tomorrow. And that's the reason. And of course, all the bioprofessionals who are associated with Biotechnica, all of you all have this potential to take this technology forward in the future. So why not start from A, which is all of you, isn't it? So that's the reason we chose this day and this time to start this session, this 6 series webinar for all of you. Now, ladies and gentlemen, boys and girls, there is some special announcements to be made. Now, these webinars will be 1 hour, sort of 1 hour, okay? And they start from today. So 26th May will be the first session. And the entire schedule is posted on the website. You can go and check it out. 26th May, first session. 3rd June, the second session. All are at 7 p.m. 15th June is the third session. 23rd June is the fourth session. 2nd July is the fifth session. And the sixth session is on 14th of July. Okay. So it starts from 26th May. It ends in July. And all you need to spare is 1 hour on these days. That's all. Okay. Now, what happens next? If you attend all these webinars, all this webinar series sponsored by Altem and coordinated by Biotechnica, then only you will be eligible to get the e-certificate. So all those people who want to earn an e-certificate, this is how you get it. At the end of every webinar series, you will be given a feedback form. You're supposed to fill that. And once you have filled, we're going to check if you have attended all the 6 sessions, and then only you'll be getting the e-certificate automatically. No questions asked. Okay. Now, I can see the entire India, right now, a lot of people watching in from different parts of the country. The only thing I would like to wish for all of you is please stay safe. Please take care of yourself and your family, because we are passing through the eye of a storm. In fact, not just one, but 2 storms, right? And while all these 2 storms, the coronavirus pandemic, on the other side, you're hearing the Yas tornado, which is, rocking the Bay of Bengal and the states there, isn't it? So people, I'm really grateful that you took out time to attend this webinar amid all this chaos which is happening, right? So I think you all deserve a hats off. You guys are the real learners, and only true learners of today can become great scientists of tomorrow, great research professionals of tomorrow. Now, guys, one request, just one small request I have from all of you. So you see, these kind of industry-sponsored webinars are very difficult to conduct, because we have to really convince the companies that please come over and talk to our research professionals, our students, our scientists, our academic professionals who are into the academia as well as industry, and talk about these new technologies, right? And they really get sad and frustrated when they see that people don't show interest, okay? People don't share their webinars, right? So this is a small request from my side, from Altem's side, from Biotechnica's side. Please share this link right away, wherever you want. LinkedIn, social media, Facebook, WhatsApp, wherever. Please, each person can invite another 2 people at least, and that will result in a great session, great 6 sessions together. And that's when entire India will learn bioprinting together, right? What's the point of having a few handful of bioprofessionals together? Why not bring in every biotechnician, whoever is around, and whoever is not from Biotechnica? Let's bring everybody around. Let's call all of them and say that, hey guys, we are going to talk about bioprinting, the future of organ transplants, right? So do I have your promise? Yes. Can you quickly share and come back? Yes. Okay, wonderful. Thank you so much, guys. And now I would like to bring up our speaker for the day. But before I add her onto the screen, I want to know, guys, are you ready to learn? Are you eager to learn? If yes, type ETL in the comment box. Let's see how many ETLs I can get in the comment box. ETL. eager to learn? How many of you are eager to learn about bioprinting? How many of you are eager to have hands-on on bioprinting, right? The future is here, guys, right here. ETL, wow, I can see a lot of ETLs coming in. Wonderful, wonderful. This is a great encouragement for all of us. So with these thoughts, now I will bring in the speaker of the day. Her name is Aishwarya. Welcome, Aishwarya, to the
Hi,
session.
thank you.
How are you, Aishwarya?
I'm great.
Is it
I'm
all
great.
good?
Yes.
Okay. So, ladies and gentlemen, boys and girls, she's going to be the speaker of the day, and she's from Altem Technologies Private Limited, and she holds a very important position there. And she is going to talk in detail about the first session, right? And then we will move on to the small question and answer session. Now, we don't know if we will get time for question and answer session. However, we will try for all that. Okay. Now, so today's topic, Aishwarya, what is the topic? Bioprinting, right?
Yeah,
What
bioprinting,
all
the
you're going
future
to
for.
talk about today?
So I'll be talking about the technology itself, how
Okay.
tissue engineering has, progressed over time
Mm-hmm.
to get to bioprinting, and
Mm-hmm.
following that, a few cases, a few examples, and obviously a product which is BioX, a 3D bioprinter. So with
Right.
this, this wraps up most of the topics
Mm-hmm.
that we want to cover.
Okay. Okay. Great. So, Aishwarya, what is your role in Altem? What exactly you do at Altem? Could you throw some
Yes.
light on that?
So I'm a technical specialist at Altem Technologies in charge of 3D
Okay.
bioprinting. So I deal with
Wonderful.
I deal with whatever cases we have related to
Right.
bioprinting, assisting researchers and scientists across India. So yeah, that's
Wonderful.
what.
So, the guys, there you have it. Aishwarya is going to enlighten us with this new technology, bioprinting, the future of organ transplants. So, let us add her screen here. The PowerPoint is right here. Over to you, Aishwarya. The next 45,
Yes.
50 minutes is all yours. I'll meet you
Yeah.
at the
Yeah.
end. All right, guys.
Yes. All right.
Thank you so much.
Yeah. Good evening, everyone, and thank you for making time to come attend this webinar on bioprinting, the future for organ transplants. I'm Aishwarya Shirur, a technical specialist at Altem Technologies. So I'll just start with an introduction of our company of Altem. So us, Altem Technologies, we are a 3D innovation platform company, and we deal with several set of products across every technology possible in 3D printing. So we start with, say, Dassault systems in CATIA, software, MSC for simulation, and then Stratasys for 3D printing, Artec 3D for 3D scanning, Dassault systems again for BioVIA, which is a life science solution and a simulation software, followed by Cellink again, which is for 3D bioprinting. So we started off at sometime about 2011, and since then we are establishing our foot in the industry, and we have attained a set of recognitions throughout the globe. So we have a couple of customers, in fact, quite a lot of customers. That's why we just slowly adding on people. And the areas where we actually work with starts from, say, education and research, aero and defense, automotive suppliers, healthcare, life sciences, obviously, consumer products, automotive OEMs. So I'll begin here with the main idea, or how do we start with? So, with the advent of time, we actually started with this concept of the bionic human. And here, this was, I think, decades ago, wherein they said that, okay, let's start getting into this field of prosthetics or rehabilitation, wherein whenever there was a deformity, there was a way of coming with a solution. Say, example, having a prosthetic arm, a prosthetic leg, pacemakers, or knee joint replacement. So these are the kind of things that we actually came up with, and that's why we have the concept of the bionic human. And from there, we actually progressed to this state wherein we now not only want to get into form and function and fit, but we're also looking at something like function, feel, form, and few other concepts which are required. That's where we started off with, our first urethra model, that is a tissue engineered urethra model, followed by a cornea which was printed, and then we have our urinary bladder, and then we have trachea, and obviously we are progressing towards making more complex organs, making more complex structures. Now these are things which are supposed to be quite realistic, or at least close to real, from the human body. And the kind of challenges we're actually seeing right now in life sciences is that we have a great amount of scarcity of human organs. There's a lack of a lack of organ transplants, or rather donors available, and we do have a lot of people losing their life. And say even after they have got a transplant, there is a case wherein they do not comply to the immunological properties. So this is just in general about healthcare, and obviously when you come to the research aspect of it, we have a wastage that is caused due to the wrong testing methods. We have drugs which have been created, but now these are tested on rat models and animal models, and this is why most of say you would say money or time has been spent on. Obviously, it's a great work that we're doing, so we are now trying to progress into something a little more closer to our functions, our bodily functions. And with these drugs which are created, you have another disadvantage, that is lab to shelf time. So we are creating these testing models, we are creating these drugs, but the time it takes to actually come out in the market is way longer. And that is where we have tissue engineering, which started. Now tissue engineering is a concept which is brought in by Langer and Bacanti sometime, maybe a few decades ago, and this is where they actually shuffled in a few things. So basically it is a interdisciplinary field where they apply the principle of engineering and life sciences towards the development of biological substitutes. And the idea behind creating these substitutes were that you would restore, maintain, and improve the tissue functions. So with this main idea in mind, so we are actually trying to like replicate something in our body in a more realistic format. So here the main essential components that we need are scaffolds, cell source, the cells that we're going to use for it, chemical and physical stimuli. So when you look at tissue engineering as a field itself, you have to go from, say, the cell sources, right? You're going to select maybe stem cells or culture the cells, or whatever that you need to do. You need to find the right environment. So that you have a bioreactor environment where you can grow your tissues in. You have a material that you need. So the chemical or physical factors is also the materials that we use to create these scaffolds. And then you have tissue architecture techniques. So the way you are going to create it, how are you going to go it? Where is it going to be a top down approach or a bottom top approach? That's why you need to decide. So this is a field which is quite a mix of multiple areas, multiple set of knowledges that you need. So when you talk about scaffolds, right? Scaffolds are the ones which are supposed to create structure, and then you have cell source, which is basically the life to it, and then you have the chemical and physical stimuli, which is creating the environment, or creating uh, the chemical structures that you need, the cell signaling if required, so whatever. And then when you come in detail to this, you will actually know that scaffolds are structures that are supposed to be biocompatible. They need to attach the cells, need to allow migration and retentions of cells, and obviously also the biochemical factors. Now, biochemical factors are these are the biochemicals which actually bring in the functions. So we need to make it essential that we have the main properties required to provide the main structure. So scaffold's job is to create a structure to give a physical support for your cells. So here, when you're creating a scaffold, you need to also consider that there is diffusion as in a proper transportation of these nutrients across the scaffold through the cells, and there's a proper pore interconnectivity. The reason why you have pore interconnectivity is because you need connection between the cells for them to communicate and to produce more of their biochemicals. So the modification of behavior of cell phase and mechanical influences is also one more thing you need to consider. After you have scaffolds, you obviously have your cell source, which is Say, for example, we are going with skin, and skin has these three main layers, which is the epidermis, the dermis, the subcutaneous layer. So when you go to the epidermis, you have keratinocytes, melanocytes, Langerhans, and Merkel cells. When you go to the dermis, you have fibroblasts, mast cells, adipocytes, and then you have the subcutaneous cells, again consisting of adipocytes and few other cells. So when you're selecting whatever application or whatever tissue you're trying to replicate, we need to select the cells which are most efficient, most required for the functions. So that's why in case of skin, you would say example limit ourselves to maybe epidermis and dermis. That's where you would go with keratinocytes and melanocytes. And in the dermis, you go with fibroblasts and adipocytes. So these are commonly used cells when you're going with skin. So obviously, when you go with a wider range or a different set of tissue, you will have different types of cells. Sometimes you can use stem cells, you can use say bone cells for bone, blood cells, muscle cells, skin cells, fat cells. So you have multiple types of cells depending on what application you're looking at. And then you have your chemical and physical stimuli. So for the chemical and physical stimuli, we're actually looking at the cell culture media. So this is the main house for the nutrition. This provides the kind of nourishment, the kind of energy requirements that is essential for your cells, and that's why we go through a set of protocols wherein you have to grow in these cells, culture these cells rather. We have to make sure that there is an aseptic environment because we don't want our cells to be contaminated. Then there is temperature, which plays a major role for us to keep it at the ideal temperature, which is 37. Then you have incubation space. So the incubation is going to take care of your temperature, your carbon dioxide levels. You have a bioreactor, which creates that physical environment, which allows the proper growth. And then you have obviously time and differentiation of the cells as well as the culture. And obviously the technology comes in, as in what kind of platform, what kind of area you are going to print it on. While you are taking care of chemical aspects, you have cell signaling and cell cell interaction. Now cell signaling and cell cell interaction, these are supposed to um, play an important role when you have the cells having a better porosity, better interconnectivity, and so these are the things that are quite essential. So we have conventional methods. So we have scaffolds which we create, right? So in order to create these scaffolds, you have conventional set of methods wherein you are actually going to create this main physical supporting structure for your cells. And there are various set of ways you can do it, where you have say leaching method, under which you have solvent casting, ice particle leaching, gas forming. And then you have microsphere method, which is where you have biodegradable microspheres, microporous beads, particle aggregated scaffolds. Then you have phase separation. So freeze drying is one of the commonly used methods that we hear about. Then we have fiber spinning method. So fiber spinning is basically electrospinning. So you're creating a nano solution of the material you want. You're going to let it pass through a difference in potential, and you're going to allow that create the scaffold you want. And then you have decellularized matrix. Decellularized matrix is basically taking a tissue itself, and you are going to now get it to a point where it has only its ECM, which is the extracellular matrix. So this is used. This was used rather. This was used before, and they used to follow these methods to actually create a scaffold. But now, when you come to the actual ways the whole process works, you have in general a step where you have isolation from the patient, right? This is where you isolate the cells from the patient. Then you have the seeding of the cells. You are going to end up putting the cells, or rather dropping the cells using pipettes on your scaffold with the cell solution. Now cell solution, obviously you need to consider the concentration of the cells you are using, and this is again optimized according to the application and the amount at which you want the differentiation to occur. So once the cell is seeded, you are going to put it into a bioreactor system, and then you have to let it grow or mature. When you take this to an actual specific application, you have to understand what part or find what application you're going to find, and then again go through the same set of procedures where again you need to consider the chemical signals, you need to check the selection of the source. We need to bring all of these together. So you need the signals to take a good part, you need the cells to play a good role, and then you also have your scaffold. So one of the disadvantages or a couple of disadvantages in these conventional methods are that they take very, very long time. So takes a long duration. They're said to be costly because once you have started your process and you have done creating your scaffold or even going through the rest of processes, there is going to be a lot of contamination, there is going to be a lot of other factors. And one of the major factors where these conventional methods are actually not the best, they are working but they're not the best, so that's where uneven distribution of cells happen. So you have your cells which are seeded on it, right? There is a chance that most of these cells do not bind well, they are just binding to the surface and then they fall off, and you do not have the full amount of cells that you required, and they are not able to get through the scaffold entirely. They need to literally get within the scaffold to create that better environment. Next is the reproducibility. If I've used a particular method to create a particular scaffold, it's very unlikely that you'll have the exact replica of it, because you're using more rather manual methods to do it. And then obviously there is another factor to consider, which is the failure to replicate the geometry. So when you're talking about the geometry, when you're talking the scaffolds or creating the scaffolds, they have a very set amount of or a set design that you can create. So with all of these disadvantages in mind, we have something more rather automated and more smart as a system to go against these basically advantages which can actually help in this process of tissue engineering, and that's where 3D bioprinting comes in. So 3D bioprinting is a form of additive manufacturing that uses, say, cells, and then you use these cells with biocompatible materials and you print living structures. The way this works is that it goes layer by layer. So it's the bottom top approach where you go from a single thing to a larger structure, and this is supposed to mimic the behavior of the natural living system. So 3D bioprinting is actually a synergy of 3D printing with tissue engineering put together. And the essential requirements here are again going to be the cells, bioinks, culture media, and few other physical and chemical factors. But coming down to say cells, we have already spoken about it. We have now a section called bioink. So bioink is actually a biomaterial which is supposed to be biocompatible. What it means is this material is actually now taken from natural sources, extracted from natural sources. Example, you have a material called alginate, which is actually taken from seaweed, extracted from seaweed. And then you have chitosan. This is taken from crustaceans, the shells of crustaceans. And they are processed obviously to come to a form where they are more usable with less contaminations. And also bioinks, being biocompatible and extracted from natural sources, are supposed to provide the natural nourishment along with the culture medias. So they are actually assisting in creating the ECM for whatever tissue you're trying to create, because they're natural, uh, they are more biocompatible, they create more of an environment, a more friendly environment for our cells to interconnect, grow in, and create whatever structure you want. So I'll just play this short video which will make it more understandable realistically.
I guess the audio is not coming, Aishwarya. So
Yes.
what you can do is there any audio in this?
Yes, there is. You're not able to hear it, is it?
No, we're not
One
getting the audio.
second.
No problem. Uh, you can continue. No, no, no. You
One
can
second.
continue.
One
No
second.
problem.
Yes, just hold on. Okay, I have enabled it. All right. Can you hear this?
Yeah. Can you
3D
click on hide? Yeah.
Yeah.
Pearson Young
Perfect.
with the Human Lab at UNC Chapel Hill. We print things all the time,
I'm
whether
just
they're done
going to
if we
take this
use
further.
3D bioprinting. Tissues and organs, we could help the hundreds of thousands of people waiting on transplant lists. This idea is not too far from reality if we use 3D bioprinting. 3D bioprinting is just like normal 3D printing, except it uses living cells as ink to create living structures. Like 3D printing, you have to create a model on a computer, then layer by layer, your living structure will be printed. The first step in the process is known as pre-bioprinting. Here, the desired product is determined and studied. Oftentimes, 3D scans, such as CT scans or MRI images, are taken of the desired product and are then converted into a series of 2D images to serve as a template for the different layers. Cells are then isolated and extracted from an organism, which is often the recipient of the product, in order to create bioink. Bioink is one of the most important parts of the 3D bioprinting process. It starts with the cells that were extracted. Then, molecules called hydrogels are added to provide water for the cells. Other nutrients and chemicals are added so that the cells can grow and communicate as if they were in a living body. Once the bioink is developed, we reach the step of doing the actual printing. Using the bioink, our organ is printed layer by layer until we achieve our final product. There's not just one method of bioprinting. Different types include inkjet printing, acoustic printing, and laser printing. The most common type of bioprinting, however, is extrusion printing. This method is probably how you would normally think of 3D printing. The bioink is loaded into a printing chamber and is pushed out a round nozzle. The nozzle produces a tiny filament that is often around 400 microns in diameter, or about the thickness of 4 pieces of paper. Once you've finished the physical bioprinting portion, the final step is solidification. In general, bioink is a viscous liquid, so in order for it to become the desired product, it needs to harden. Sometimes the bioink will solidify on its own. Other times, the process of cross-linking will occur with the aid of things like exposure to UV light, physical changes like heating or cooling, or chemical changes due to the addition of certain compounds. In a way, 3D bioprinting is very similar to making a cake. First, you have to pre-bioprint. Similar to the medical scans that are used, you have to use a recipe to model your cake after. Instead of using bioink made of cells, hydrogels, and other chemicals, you make a cake batter with eggs, flour, sugar, and other ingredients. Then, you create your cake layer by layer until they all come together, just like when 3D printing. Finally, the solidification process is like putting your cake in the oven and letting it harden to achieve the desired product. As the technology of 3D bioprinting continues to be developed, more and more advances are made. Currently, we aren't quite able to produce entire organs due to the complexities of the tissue, but there have still been uses of 3D bioprinting. For example, a tracheal splint was created for an infant with TBM, and bladders have been constructed for those with end-stage bladder disease. In fact, a rabbit-sized heart was even created in 2019. Other applications of bioprinting can be creating artificial organs, bone tissue regeneration, aiding in cosmetic surgery, and producing living tissue that can be used for pharmaceutical testing without the risk of harming a test subject. In fact, 3D bioprinting is being used to create drug delivery systems that respond to stimuli such as pH, temperature, and light. Thank you.
So he gave a very elaborate, or rather simple example of how it works. So there are a lot of examples right now going on wherein, and in fact, some news coming up saying some people developed ceramic based inks to 3D print bone parts with living cells. Scientists have combined 3D bioprinting and computer modeling to study cancer metastasis in blood vessels. Um, Obviously there is a partnership among people with liver organoids, creation of heart models. They have created this very small heart model, and soon they plan to take it to a larger scale with obviously development. And healing, say wound healing, is another sector that we are dealing with. And blood vessels and other parts have been created. So the types of bioprinters, he's also mentioned it in that video. There are inkjet based, laser assisted, extrusion based, and stereolithography based. Among all of these, the ones that are predominantly used are extrusion printing, and extrusion printing is actually pressure assisted. So this requires mechanical pressure, or say rather air or any vacuum, to create or to allow the extrusion of the ink. And this can allow multi-model printing, and you can use any types of material, multiple types of materials together or even separately. So then you have the digital light processing. So the digital light processing is more like stereolithography method here, except you're using projection of light layer by layer. So what this does is, it is a light assisted printing. It is filament independent because now you're printing it layer by layer. It's supposed to have high resolution, limited material usage. So just play this small video in general on extrusion printing. So then you have the light processing. So there's a continuous light projection that happens in the bottom through something called a vat, and that's the kind of structure that you get. So very complex and watertight structures can be created. Coming down to the steps involved a little more in detail. So now if you're taking any specific application, you would have to find the anatomical structure of it first, or at least have a basic idea or image of it. That's why we start with imaging technique as a first step, wherein you either use X-ray or CT or MRI or even 3D scanning as a procedure to attain the data, or rather attain the structure that you require. From that, now you make it into a digital format, right? So it's into a system. You now try to create this system which shows the data in 2D and convert it into a 3D format. So that's where you have the design approach, wherein you're converting all of this data using CAD modeling softwares, say example Mimics or any other software, where you take the CT or MRI images and you convert it into a 3D format. From this, you're going to make the design obviously for the machine to understand, and uh, That's where you have using something called STL file, which is a CAD model file, converted into something called G code. So G codes are basically these slices converted into a more understandable language by the machine. While you have done that, the next step is going to be the material selection. So under the material selection, you have the synthetic polymers, natural polymers, or ECM. So when you're using for bioprinting, you generally tend to use natural polymers and in some cases synthetic polymers. You can select among maybe collagen or alginate or gelatin based on the properties, um, based on what is the aspects you require in it. So another addition to material selection is not as simple as it sounds. It requires a lot of work because when you're taking a material, you are trying to look at something called the printability, the shape fidelity. Printability is how well this prints, and shape fidelity would be something like after it has printed in a specific temperature or specific pressure condition, you need to see that it has attained its shape fidelity or it has attained the shape it is supposed to attain. So if it's too liquidy, if the liquid or the bio ink is too viscous, then it will not extrude at all. So it needs to have a specific viscosity so that the flow is correct. And we also need to consider how the shear strength or the shear rate affects it. With the material selection, also we need to see how well a particular cell can combine with it. So you use maybe differentiated cells or pluripotent cells or multipotent stem cells. While you have combined these two, there's another process which is the processing part of it. Processing as in what technology, what mode are you going to use to make the print. So you have inkjet, micro extrusion, laser assisted. So we would select among these and then carry out our print that we need to do. And then comes a process where you have um, the maturation of that. The tissue, so basically it's a cell which is growing and now it's converting to have a tissue like function. So it needs to go through a phase of incubation, it needs to go through a phase of evaluation, and we need to see that these cells that are implanted into this design that you have created has to have a good amount of cell viability. Cell viability would mean that the cells are live. So we do live dead assays, and we do a lot of immunostaining. We might have to do a lot of histopathology in order to just test and see how well they are functioning. And while these are going through the phase of maturation, we also go through a couple of in vitro tests, again, which involves maybe mechanical testing, young modulus testing, whether it after stretching does it entirely break or does it have an amount of elasticity, because we're trying to mimic something as similar to what we have in our body. And if you notice that most of our parts of the body have a specific shore rate or a shore value. So we need to consider those. And following this state of maturation involving all the tests comes a point where you make a decision whether you can implant this onto an animal for an in vivo study and then carry out with the rest of the processes. So I will talk about a few cases wherein they have used extrusion based printing to create, for example, here a cornea. So to create a cornea, we know the structure of cornea in general. The general idea about a cornea is how it looks like a lens and how it is concave in structure. So we now have to go through the processes where you have a digital model of the cornea obtained and the corresponding 3D printing code is exported. So this is done. Following that, you have biomaterial and cells combined together to form the bioink, and then you have your bioink mixed with the respective cells, and then you go with the printing. Now the printing part, you see this green structure here, this is just the main CAD model. Following that, you go through a process of creating the G code, as I mentioned. So that's where you slice the image. And when you are creating this sort of structure, you need to create a design so that the machine or the tool actually follows a specific path and creates that structure that we need. We convert it into G code, and following that, we carry out the process of printing. Now here they used support structure because it depends again on the thickness of what you're trying to print. We have to print the layers together so that they also have a mechanical strength. They have to be able to stay as it is. Now, the thinner you make it, the more amount of support would be required. So they used a support structure, they printed it over it, they lightly took it off that, and then they did the processing part. So this was where they were able to actually replicate the cornea, and this was done in Newcastle University, and they've attained a good amount of success in terms of viability, and as well as they have carried out some in vitro tests following that. Next is bony structures, or the process of complex bony designs. So in this paper, or rather this case, they had to use bioceramics, right? So while using bioceramics in general, when we talk about bioceramics like hyaluronic acid or so, we actually attain these materials in the form of beads or in the form of any other general design. And now we are trying to look at it as something more customizable, more specific to a patient. That's where you will have to go through a lot of processing to actually chisel that out and make it into a structure we require. That's where you have a replacement, a better replacement, which is 3D bioprinting, which can create that design for you. So for that to happen, we need to create a rather slurry or a biomaterial composite of hyaluronic acid or hydroxyapatite, and then you have to create a more viscous bio ink, which can print well. And once you have printed it, it needs to go through this processes of maturation, or rather cross-linking process, where they solidify. So while you do that, you need to do a couple of optimizations there. So to optimize it, we go through tests of, say, doing the infill density test. So infill density is actually it's like you take a solid and you're trying to fill that solid structure with ink or something. So either you have it spaced close to each other or far from each other. So far from each other would have been 50%. If you were to make it a little more closer, 75%, and then you go to 100%. So these tests were carried out where they would optimize and understand what if infill density would create better mechanical properties and better development. So the optimization was done, and now they use this optimized hydroxyapatite, and they go into creating your application. Your application here would be a person with a fracture in his wrist, or rather the radius ulna bone, right? So this person has a fracture here, and now you need to obviously go through the process of CT scan or X-rays. Here they have taken a CT scan, and now what they've done is they've segmented it, right? They've taken that data from the patient, they have segmented that section where they need to add a graft. So graft is an external body or an external structure you're going to add. They would create that design. You need to create that model saying, okay, this is the kind of design I need, and this is the CAD file I need in order to do the reconstruction. So once you have attained this CAD design model, you now go through the process of printing the same structure, like using a 3D printer or like using a 3D bioprinter. So you also go through a process wherein before doing a surgery, so we are adding a graft, so we need to go through a process of surgery. We can also go through the step where you can have a 3D printed, a rather plastic 3D printed model of that structure, that graft you want to create, print it, use it on a rather hand model which is now artificially created using a 3D printer. Try to practice your surgery in order to again do the pre-surgical modeling, and following that you go to a point wherein you will now actually go with using the graft. So they use that, and they obviously stitch it up, do undergo the procedure, and now they check it. So they have attained a good amount of success in this graft quality. Now it has also not had any immunological defects here, and it supported and helped the growth of the bone. From here, we have in general tissue models, right? So we are coming to a point wherein we are trying to create more transplantable models. we need more organs that we are artificial organs that we are trying to create. So with that, we would actually go with using a heart model initially, studying it, and then going to this phase wherein it goes from a single patch to a gigantic heart, or say the heart the size of our wrist, right? So we would go with again the blueprint, the design, the biomaterial. So here we used bioink which is cell ink laminate, and we used IPSC cells. We used the bioprinter, printed the structure. See, they have created a very simple heart-like structure here with few set of layers, incubated it, and then they found that after 3 weeks of culturing, they would see quite viable and lively cells, and you could see this as a heart model. So the result actually led to um, you see this influx and outflux. This is actually influx and outflux of calcium, which is the main essence of our heart tissue, our heart cells. So they were able to find a good result in terms of using iPSC cells and using bioprinting as a process, which will allow creating a more viable and a more realistic model of heart. The next example is an alternate to autologous cartilage for auricular reconstruction. Now, this is a case wherein you have a rabbit with a deformity in his ear, and you're trying to find the best regenerating best regenerating implant. So either you go with the autologous cartilage, either you go with a scaffold which is generally created with a tissue engineering concept, a conventional method, or you go with a 3D bioprinted cartilage. So we went through this process wherein you either went from autologous, that is its own cartilage, following a seeded cartilage, and then a 3D bioprinted cartilage, and we were able to find a good amount of regeneration in the 3D bioprinted cartilage, in converse to the autologous or the scaffold seeded cell seeded cartilage. So you would see that there's a great amount of cell viability and the regeneration of the cartilage cells. With this, I will just show a small demonstration of the machine, what it does in terms of these cases, how you are going to, it's more like a complete flow of the whole process, which makes this better to understand. Pressure, temperature controls, speed control again, another factor, and photo curing. So We would, one second. Yeah. So this is actually a solution by Cellink, and Cellink is a life sciences company providing multiple solutions, and you'll get a fair idea here with this video here on Cellink.
Over the last century, the human race has made tremendous strides in healthcare, driving forward the quality and length of life on this planet we call home. Despite these extraordinary advancements and scientific breakthroughs, there are massive burdens on our healthcare systems, and we still find ourselves treating the symptoms rather than the disease. These challenges require a more holistic approach. Bioconvergence is where nature and science intersect, where advancements in biology and technology can unlock the door to things like personalized medicine and organ regeneration. As the leading bioconvergence company, Cellink offers exactly that. Technologies, systems, materials, and expertise in the key areas of the bioconvergence revolution equip researchers to answer the most pressing questions and enable this brighter future. Cellink provides the tools for a bioconvergence workflow from early-stage development to large-scale manufacturing. Such tools provide the potential to help doctors customize cancer treatment through omics-based tumor profiling, miniaturized drug delivery, and tissue replacement. The potential to enable the regeneration of neurons and tissues for treatments that can change lives. The potential to measure the activity of a patient's muscles and brain as they go about their daily lives for early detection of neurological diseases such as Parkinson's. By democratizing advanced research tools, we provide researchers with a fresh perspective to find answers and empower them to leverage the potential of precision engineering, automation, and artificial intelligence. This will propel us forward to the future, a future where personalized medicine is no longer a dream, but a reality. Join us on this journey to create the future of medicine.
So the Cellink solutions that we have has something called Incredible Plus, the Bio X6 series, the Bio MDX, and Luminex. So they go with your extrusion based printing as well as your light based printing, which is Luminex. So I'll also talk a little bit about one of our other solutions, that is BioVIA. It is a simulation suite, and this BioVIA is from Dassault Systems, and this is meant to help in drug discovery, in regulatory functions, in pharmaceutical industries. BioVIA solution creates a scientific management environment, and this bridges the network environment for materials, biological, and chemical innovation. So this is an entire profile of in silico testing and in silico analysis of any drug delivery or drug development that we need to do. So we have a basic portfolio of about, these are all of the softwares that come within. We mainly focus on Discovery Studio, Material Studio, and Pipeline Pilot. And Discovery Studio is a comprehensive software for analyzing and modeling molecular structures, sequences, and other data which is relevant to life science research. So it involves things like homology modeling, protein-protein docking, virtual screening, fragment replacement, protein engineering, ADME, and toxicology studies. And we also have Material Studio for computer-aided single model designs for solar cells, polymer studies, lasers, and few other requirements wherever essential for material science. So thank you so much, and you can say or ask whatever questions you wish. And this is the end of the session.
All right. Thank you so much, Aishwarya. That was really insightful.
Yes.
So, people, how was the session? Did you like it? Please let us know in the chat box quickly. Yes? Okay, wonderful. So now we will start our Q&A. But before that, there are some questions about the PowerPoint. I'm not sure if that can be shared because that will be obviously a confidential property of the company. However, if it is possible, we'll let you know in the future. Okay. So let us start with the Q&A, but we will have to limit our Q&A to, I guess, 5 minutes because we are already out of time. Okay, guys? So whatever is the most important question which you have to ask, and we'll randomly pick only 3 questions because we are running out of time. However, in the next session, we'll definitely try to pick your questions early. Okay? So let's start with the Q&A session. Okay, so let's see what are the questions we're getting. So how you're going to type the question, type Q and then the question, okay? Q and then the question. Whatever is the first question comes in your mind, please go and ask. In the middle of this, let me go through the previously asked questions. One of the questions which I saw was from Kirtana, and she had asked, are these products available in India? So over to you, Aishwarya.
Yes, definitely. So we are Altem Technologies in India. We are partnered with Selling, and we are the main distributors of the bioprinters. So these ranges of products that you see are available definitely in India. And people, say example, IISc, IITs are working on using these machines for their progress in research.
Okay. So this is the next question which is coming in from... Okay, as soon as I read the question, it goes up. Hold on, guys. Let me read the question first. Okay, what's the future of bioprinting? That's the question.
So we have now started with creating basic tissue models, models without even cells, models with cells. We are now progressing towards creating vascular structures, then complex structures, and then finally creating maybe organs, right? So our main idea behind all of this is creating organs. So we are far from it, but we are also getting through research to that point.
Yeah. Okay. Another question, what is the material which is used for bioprinting?
Okay, so here we use biomaterials. Biomaterials are biocompatible materials, and these materials are things like alginate, collagen. They're viscous materials mixed with cells or without cells. So the materials here used are something called bioinks.
So the next question, Prachi asks, what are the chances of the model failing?
Well, now see, this is all dependent on the person who's handling it, and obviously the viscosity of the material you're using. So if you have used a material and you have done the cross-linking efficiently, then the chances of it failing is less. So along with that, there is also another factor you need to consider, which is cell viability. So if you keep all of these in check, failure would be less than 10%. Otherwise, the success over here is 95.
Okay, so the next question is about pricing. How costly is this product? How exactly it is priced?
Yeah, so 1 second. Abhishek, you think you can answer this for them? So this is my my senior application engineer. He would answer this question.
Hi, everyone. The good news is that the machines are not so expensive, so you can get away with a more entry level machine at a price of about 10 lakh rupees, which is not the cheapest thing, but considering the potential and the value it can bring to organ research, it's not too much of a big price to pay. The other end of the spectrum can go very, very high depending upon how much capability you would like to add on to the machine and how big sizes would you like to print. So I hope that answers your question.
All right. Thank you, Abhishek, for coming in at the right time and telling us the right price. Great. So moving on to the next question, we will just look at, okay, there are a lot of questions and we are running out of time. In fact, I myself personally felt this was very nicely explained by you, Aishwarya. We loved the way you explained, and the interactive videos which you have included has given a very clear picture in the minds of people. And while I'm speaking, I'm also looking at the questions. Okay. Probably have to scroll up. Okay. I don't know if this question is relevant. Robin asks, what are all the barriers we have to overcome the microbial development during bioprinting?
All right. So one thing is the machine that we have is consisting of HEPA filters, right? These are the filters to avoid any microbial contamination. So they consist of two of those, and we also have a UVC germicide light, which can allow purging this chamber of printer. And along with that, if you feel like you want to increase the security more, you would have to use a laminar flow chamber. Chances are high depending on the environment. So if you have controlled these environment, then you can at least take care of this microbial contamination. So I hope this answers your question, Robin.
All right. So we have another question coming in, and that's from Akshaya Kar. And she asks that how is 3D bioprinted scaffold of an organ more beneficial than a decellularized organ scaffold with respect to organ bioengineering?
Okay. So one case is when we were using decellularized scaffolds, they would use maybe an animal tissue, and then they would go with decellularizing it and then using it, right? Now we're looking at something wherein we want to create this for humans and maybe make it more customizable. So if you're looking at that, where do you attain that tissue from, right? Now, if I'm putting it for a specific human and I want it to be more autologous, so I would not go with taking a decellularized organ scaffold. I would rather create a scaffold artificially for that person. So that's where 3D bioprinting will actually, take away this gap. So it all depends on the size of what you're trying to recreate, what you're trying to graft. So I hope this answers your question.
Okay. Nice question, Akshay. Right. So I think we'll just take the last question of the day because we are running out of time. And don't worry, in the next time we are going to take up all your questions. So it is from Rishabh. He asks, how useful is bioprinting to study microorganisms, which shows high frequency of mutation and antigenic variation to produce vaccine and drugs?
Okay.
Over to you.
So this tissue that we are going to create, right, is used extensively for applications of drug testing as well, right? The models we create can be 3D cell culture models, or they can be just basic disease models that you can use. This creates a good platform for testing whatever the type of issue, whatever type of problem you want to test. May it be a microbial test, or it could also be a drug test. So this creates that platform, and this is a tool which assists in it. So yes, it definitely comes to that question which you ask.
Mm-hmm.
All right.
Right. Thank you so much, Aishwarya, for your time and all the knowledge which you have shared today. And people, I know you have a lot of questions. I can see a lot of questions. In fact, my heart goes out to you. I personally feel that we should spend 2 more hours answering your questions. But, there is a time limit which we have to respect, okay? But don't worry, you have 5 more sessions to ask all your questions. So definitely you will get a chance. Now, most of you have been asking about the feedback form, and of course, you want to put in your attendance. Before that, I have a request. At Biotechnica, we want to become a part of your career, your journey towards life, and what best it can be if you all are in my LinkedIn network. Okay. So just go on LinkedIn, type Biotechnica. You'll definitely find me, and you'll definitely find Biotechnica's fan page. Please like us there and follow us there so that you can be updated with all the latest things which are coming up. Okay. No matter which organization you represent today, you are definitely going to be enriched by all the knowledge which people like Aishwarya, companies like Altem and Cellworks are going to share right here in this platform. Right now, people, this was the first session. Okay. Now, that means there are 5 more sessions where more knowledge is going to be transferred. Right. So don't forget to attend the next session. Let me repeat. It is on 3rd of June. It's a Thursday, and it will be at 7 p.m. And the next topic is organ on a chip and soft robotics with bioprinting. And again, it will be presented by our expert Aishwarya Shirur, and she'll be right here to answer all your queries then again. Now, this live stream will be there on our YouTube channel for you to refer back again in future. And one very important thing, if you do not fill the feedback form, which will be given in the chat box right now, then you will not be eligible for the e-certificate. So please make sure you do that. Okay. So with these thoughts, we will conclude here. Thank you, Aishwarya, and thank you,
Thank you
Altem,
so
for
much.
taking out time from your busy schedule and interacting with our subscribers. Each time I get a chance to interact with your team, I really feel enriched, and I come back home saying that, okay, I learned something. And today, again, that is a takeaway, Aishwarya. Thank you so much. I'm really grateful on behalf of all our subscribers and fans and members of Biotechnica. I would like to express my gratitude and tell you that we all are truly grateful to Altem for this wonderful session. Now, guys, feedback link should be shared with you shortly. Let me check if it has been shared. Okay, it should be shared. Let me check. Hold on. Okay, here you go. Okay, so the feedback form link is shared. Please check in the chat box. Okay, and I'm going to send you an email. Please share your feedback there as well. Okay, I'll probably share my LinkedIn profile link there as well so that you can connect with me. Okay, so that's all, guys. I hope everybody has got the feedback link. I know you have questions. Don't worry. We'll answer them next time. Thank you, Aishwarya. Good night, everyone. Trust me, this was one of the most enriching sessions we ever had. Okay. Thank you so much. Good night, guys. Bye-bye.